Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about the three laws of thermodynamics. Now, the first and third law of thermodynamics is pretty easy. In fact, the first law of thermodynamics is probably taught in junior high, where you learn that energy cannot be created or destroyed. Energy has to be conserved, and that's going to be our first law of thermodynamics, which most people kind of like widely accept even before they get into a chemistry class. Okay. Now, the third law is about entropy. I don't think you learned about entropy before chemistry. And entropy is a measure of disorder. And what the third law of thermodynamics tells us is that the only time that you have zero entropy, like no disorder whatsoever, is at 0 Kelvin. Now, in the previous lesson, we learned that solids are going to have the lowest entropy, but even the solids, they're vibrating and rotating against each other, the molecules are, and therefore there's going to be some disorder, okay? And the only time you get to zero disorder is if you remove all of the thermal energy and these molecules start to slow down and their vibrations start to slow down. And if you remove all of the thermal energy at 0K or absolute zero, the molecules will be perfectly aligned. There won't be any vibration or rotation anymore, and you'll have zero entropy or zero disorder. Okay, so that only happens at a ridiculously cold temperature, absolute zero, which is 0 Kelvin, not 0 degrees Celsius, 0 Kelvin, which is equivalent to negative 273 degrees Celsius. So a ridiculously cold temperature where all the thermal energy has been removed from the substance. Okay. Now, where we need to spend the most time is probably on the second law of thermodynamics, because it's the hardest of the three to understand, and it deals with the delta S, or the entropy change of the universe. Okay. Now, the second law of thermodynamics says that in most situations, okay, that the delta S of the universe is going to increase. And that's because our universe is expanding. And as our universe expands, there's more microstates where everything can be placed, okay? And therefore, an increase in the amount of disorder for the entire universe, okay? So remember, we're always talking about the universe here. Now, the delta S of the universe is a combination of the entropy change of the system and the surroundings. And as a chemistry student and teacher, okay, we tend to focus in only on the delta S of the system. And that system tends to be a chemical reaction most of the time in chemistry, okay? Now, the second law of thermodynamics is not about the system, it's about the universe, okay, which is the combination of the system and the surroundings. And if this is always increasing, okay, well, whatever this is, okay, this might also be a contributing factor to make this a positive number, because according to the second law of thermodynamics, that delta S of the entire universe is going to increase. Now, we could have a system that's decreasing, okay, its entropy. And what I like to talk about is like maybe like organizing your room, or, you know, like if I take this, right, where it belongs, this is like organized, this is where it belongs on this level, but if I just, you know, push it off, okay, it's now disorganized. There's more entropy now in my room. Now, to clean my room, I'm going to pick up the marker and put it back where it was, okay, but that wasn't a reversible process, okay. To be a reversible process, I would have to do the exact opposite. So if I did this to knock it off, I would have to do this to be reversible, okay? And this is not, the marker's not coming back up. It'd be a really cool magic trick if it did, but it's not. I actually have to bend down, use a lot of energy, and pick it back up in order to put the marker back into its original place where it's organized, okay? So when I did that, yes, I decreased the entropy of my system, and this would be kind of like my room, okay? I made it more organized when I bent over and picked the marker up. I made my room more organized so the disorder decreased. But to do that, I expended a lot of energy bending over and picking it up, and that's all the surroundings. So this is probably just a super a larger positive number. And when you add these two numbers together, a small negative number plus a large positive number is going to make the delta S of the universe be positive, okay? So that's the second law of thermodynamics, is that the delta S of the universe, okay, is typically getting larger, okay, or it's going to be greater than zero, okay, for processes, okay, that have direction, okay, and we typically would call that an irreversible, okay, that's an I right there, we dot it, okay, an irreversible reaction, okay, so temperature comes into play with all this. Like, let's say I have some solid water and I want to turn it into liquid water. Now, it has this direction, okay, solid to liquid, when I am above 0 degrees Celsius, because 0 degrees Celsius is the melting point of water. So if I'm at 0 degrees Celsius, okay, going from solid water to liquid water has a direction, okay? Solid water is always going to become liquid water when your temperature is above 0 degrees Celsius. Of course, we could write the opposite to be true. Liquid water going into solid water, okay, if we're below 0 degrees, that would be the direction in which it would flow, from liquid water to solid water, right? Well, there is a special situation for the delta S of the universe, okay? And that is when we go from like solid to liquid, but I use an equilibrium arrow instead, okay? I'm a little sloppy here with my S's, so let me clean that up. Okay, but this is an equilibrium arrow, which means that it can go in this direction or it can go in this direction. And that's when you have a reversible process, okay? That's when you can use this equilibrium arrow, and it's a special situation, okay? Now, this only happens at 0 degrees Celsius, okay? No other temperature can solid and liquid go in both directions, either melting or freezing, okay? So that only happens at 0 degrees Celsius. But if you have that particular situation, the delta S of the universe can be 0, okay? In these other situations, the delta S of the universe, okay, is going to be greater than 0 because there is direction, okay? So if there's direction, okay, the delta S of the universe is going to be positive because it's irreversible. Like, you can't change solid water to liquid water if you're above 0 degrees Celsius, right? Okay. So for reversible reactions, the delta S of the universe, okay, can be 0, but the special situation is that it has to be a reversible process, okay? And that's going to happen at a particular temperature for a particular chemical reaction, okay? So those are the three laws of thermodynamics, okay? Law number 1, energy is conserved. Law number 2, the delta S of the universe typically is going to be always increasing because the universe is constantly expanding, but there's a special situation where it can be 0 for reversible processes, okay? And then the third law of thermodynamics is that at 0 Kelvin, you'll have 0 entropy, okay? If you found this content helpful in determining the differences between the laws of thermodynamics, please give this a like and subscribe. When you add that comment, it really does push the information to other students that might be interested in learning chemistry.